Hello and welcome back to another IB Math speedrun with me, Vince. In this speedrun, we're going to be going over chapter 3.4 of the IB Math textbook, which is all about the fundamental theorem of algebra. So let's jump right in. So, what is the fundamental theorem of algebra? Well, we've been covering a lot of polynomials, and the fundamental theorem of algebra refers to the existence of complex zeros in a polynomial. And it says any polynomial, say f of x is equal to a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, all the way until a to the 0. What it says is that if all of these have real or complex coefficients, then this polynomial has at least one zero. And so there is some number that is part of the complex number, and remember, real numbers are also part of the complex number set, such that the value for the polynomial of this root is equal to 0. So therefore it's a root. There's at least one root. And so there's a lot of things that we can derive from this. For example, because of that, it's possible to write any polynomial in factor form. So we can write any polynomial as a combination of its factors, say a to the n times x minus a 1 root times x minus another root times x minus a third root, and so on until the degree of the polynomial, such that yeah. And so one other thing we need to talk about is something called multiplicity, because of course in any polynomial it's possible for a root to appear more than once. Say we have x minus w squared. This means that this root appears twice in the polynomial, and so we say that this root has a multiplicity of 2 if it appears twice. If it appeared 3 times, in this case, then it has a multiplicity of 3, and so on. And so if we add up the multiplicities of each root, we should get the order of the original polynomial. Say if we have this root here and we have another root, this multiplicity 3, this multiplicity 1, so therefore the original polynomial should be of order 4. Okay, and then finally we need to talk about the conjugate root theorem. And the conjugate root theorem states that for any polynomial f of x, if we have a complex number, 0, z, then its conjugate will also be a root. So it means that if we have a complex number, its complex conjugate will also be a root. And this of course is true for real numbers too, since real numbers are complex numbers, but the conjugate of a real number is the same number, so it doesn't matter. With that being said, let's jump into some questions. So, the first question we have is, I'll do the odd ones. We have, find a polynomial of the smallest degree with integer coefficients whose zeros are, and first is 0, 2, and 7, and third it's -1, -0.5, 2, and 5. Okay, so we know that in any polynomial, if it has these roots, these have to be factors of the polynomial. So in this case, x minus 2 and x minus 7 all need to be factors of the polynomial. Since we need to find the one with the smallest degree, it means that we should just use these 3 factors, since adding any other factor would raise the degree by 1. So we can simply multiply this out. This would be x times x squared minus 9x plus 14. So the smallest polynomial is equal to x cubed minus 9x squared plus 14x. So that should be correct. Sorry about that, I'm back, and so let's move on to the next question. And so, oh wait, I just erased can I go back on that? There we go. So anyways, we need to find the polynomial with these roots down here. And again, we can just take each of these as factors of the polynomial. X plus 1/2, x minus 2, and x minus 5. And so we can multiply these all together to find the polynomial with the smallest degree. I'm going to save x plus 1/2 to be the last one. So what we have here is x squared minus x minus 2 times x minus 5. So this is equal to x plus 1/2 times x cubed minus x squared minus 5x squared, so minus 6x squared, minus 2x minus 5x, no, plus 5x, so this is plus 3x plus 10. Okay. And so finally, finally we need to multiply this to that. So we should get x to the 4 plus 1/2 minus 6. So this is minus 11 over 2 x cubed plus 3 minus 3. So that's just 0x squared. Plus 10x plus 3 over 2x. So it's plus 23 over 2x plus 5. That's what I got. Oh, sorry, I forgot. It said with integer coefficients. So what we can do to get integer coefficients is multiply all of this by 2, since multiplying it by 2 won't affect the degree of the polynomial. So 2x4 minus 11x cubed plus 23x plus 10. So that should be the answer. Yep. And on to the next one. And so the next question is asking us to find here. So find a polynomial of the smallest degree with integer coefficients whose zeros include, and it's -1, 0.5, and the cube root of 3. Okay, so how are we going to do this? So we know that x plus 1, x minus 0.5, or 1/2, and x minus the cube root of 3 must all be factors here. But how do we make them have integer coefficients? Well, if we have 1/2 here, we know that we're going to have to multiply it by 2 to make, actually, let's save that for later. But what about this? So in order for this to become an integer coefficient, well, we need to put this into the form where we have x cubed minus y cubed. And so we know we can factor this into, I think it's x minus y times x plus 2xy. Is it x plus xy plus y, I think? Yep, that's correct. Sorry, x squared plus xy plus y squared. So if we have this part, then we can put this as x minus the cube root of 3 times x squared plus x times y, so that is plus cube root of 3x plus 3/2 the cube root of 3. And so all in all, this is just saying that this factor will become x cubed minus 3. And so now we can multiply it to these other two. So let's see what we get. So let's multiply it to x plus 1. So we have x to the 4 plus x cubed minus 3x minus 3. And so we can multiply this to x minus 1/2. So we have x to the 5 plus x to the 4 minus 1/2 x to the 4. So plus 1/2 x to the 4 minus 1/2 x cubed minus 3x squared plus 3 over 2. That's what it looks like. Oh, sorry, I've forgotten the x term. So this would be minus 3x. So minus 3 over 2x plus 3 over 2. And so now we can multiply this all by 2, so they have integer coefficients. So we have 2x to the 5 plus x to the 4 minus x cubed minus 6x squared minus 3x plus 3. So that should be the polynomial with the smallest coefficients that has all of those roots. Yep, that's correct. Smallest integer coefficients. Okay, and on to the next one. So factorize the following polynomials and check your answers using a calculator. So we need to factorize f of x is equal to x cubed minus 3x squared plus 4x minus 2. We need to factorize this polynomial. So I'm not exactly sure how the book wants us to do this, since normally, in a polynomial with in a polynomial of order 3 or higher, you normally get like a hint, say like they'll give you a hint that, I don't know, root equals x equals 1 or something like that, but they don't. So I don't really see a way to check for the roots aside from using a graphical calculator. So that's what we're going to do right now. So let me just get out Desmos. Here. So let's graph our equation. X cubed minus 3x squared plus 4x minus 2. Oh. So as you can see, we have one real root, which is at x equals 1. And so we can use that to factorize this. So we know that x equals 1 is a factor, so we have x minus 1. And so we need to synthetically divide this by 1. So we can do that. This is 1, negative 3, 4, negative 2, 1, 1, negative 3, negative 3, oh, sorry, wait. Negative 3 plus 1. Sorry, this should be negative 2. Negative 2. 4 minus 2 is 2. Minus 2 plus 2 is 0. So as you can see, it perfectly divides it into a polynomial of x squared minus 2x plus 2. So that is how we can factor this polynomial out. Okay, and on to the next one. We need to factor out the polynomial f of x is equal to 2x to the 4 minus 5x cubed plus 11x squared minus 3x minus 5. And yeah, again, I'm not sure how they would factor this without a calculator, so let's punch it in. Minus 5x cubed plus 11x squared minus 3x minus 5. And so as you can see, we have two roots here. One is at negative 0.5 and one is at 1. So we can use this to factorize it. So since we know x plus 0.5 or 1/2 and x minus 1 are factors, we can synthetically divide this twice. So we have 1/2, negative 1/2 I mean, and we have 2, negative 5, 11, negative 3, and negative 5. So 2 being 2, this becomes negative 1, negative 6, 3, 14, negative 7, negative 10, and then we have 5, so 0. So that factored out perfectly. And so now let's synthetically divide by 1. So we have 1, so we have 2, 2, negative 4, and then we have 10, sorry, this should be negative 4. 10 here, negative 10, and that should be 0. And so we're left with 2x squared minus 4x plus 10. So the remaining factor is 2x squared minus 4x plus 10. So those are our 3 factors. Nice. Okay. And then on to the next question, where we have, in each case, factor k is a 0 with multiplicity n and of the polynomial f. Okay, cool. So we have k is equal to 2/3. So we know 2/3 is a factor of the polynomial with multiplicity 2. And the polynomial is f of x is equal to 9x cubed plus 24x squared minus 44x plus 16. And this is more of a question I would expect to get, where we have one root, or in this case 2 roots, and we need to factorize the polynomial. That's not too hard. So what we can do here is, since this is of order 3, we can simply synthetically divide twice by 2/3 to get the resulting polynomial. So 9, 24, negative 44, and 16. Okay, cool. 9, 6, 30, 20, negative 24, 2/3, 16. And as you can see, that factored out nicely. And so let's factor out 2/3 again from this polynomial, since it has multiplicity 2. So this is 9, 6, 36, 24, and then 24 minus 24 is 0. So our remaining factor is 9x plus 36. That's cool. So this polynomial factors out to x minus 2/3 square times 9x plus 36. So that's all good. Yep. Okay, and then on to the next one, where we have to factor. We're given that one of the factors, which is k, is equal to negative 1/2. The number is equal to 3. So the multiplicity is equal to 3. And the polynomial is equal to 8x to the 4 plus 20x cubed plus 18x squared plus 7x plus 1. Okay, so this looks relatively simple. Let's synthetically divide this polynomial 3 times by negative 1/2. So we have 8, 20, 18, 7, and 1. So first, let's go 8, negative 4, 16, negative 8, 10, negative 5, 2, negative 1. And then as you can see, this becomes 0. So that's 1. So let's do it again. So we have negative 1/2. So 8, negative 4. Oh, sorry, I mean 8. Oops. 8, negative 4, 12, negative 6, 4, negative 2, 0. Nice, and then let's factor this once more with negative 1/2. So we have 8, negative 4, 8, negative 4, and 0. And so we're left with 8x plus 8, which is cool. So we know this factors into x minus 1/2, plus 1/2 cubed times 8x plus 8. And if you're following along with the book, you might be wondering why is the mark scheme a little bit different. Well, it's just because they're trying to make all of these factors, or integer coefficients. So what they're doing is we can say this is equal to 8 times x plus 1/2 cubed times x plus 1, which is also equal to, let's cube root 8 and multiply it in here. And so that's equal to 2x plus 1 cubed times x plus 1. So it's the equivalent thing. Both answers are correct. So yeah, that's all good. Okay, on to the next question, where we need to find the remaining zeros given a complex 0. So the first question is we're given this function f of z is equal to z cubed. So z we use when denoting complex numbers, minus 2z squared plus 4z minus 8, and z is equal to 2i. And so the thing is, we know that 2i is a root, but we also know that negative 2i is the root, since the complex conjugate of the root is always another root. So if we multiply these two together, we get z minus 2i times z plus 2i. And so we should get z squared plus 4. Okay, and so now we can factor this. I mean, I guess we could, imaginary numbers, it's probably just better to divide this. So we can already look, the coefficient here is z cubed, so that means that it's going to be z, just a plain z. And then we can look at the last coefficient, which is negative 8, which is going to be minus 2. So we know that this can factorize into z squared plus 4 times z minus 2. Did I cheat too hard there? Let's just check this, because it might be another complex root. So we have z cubed 4 plus, yeah, I think I cheated too hard, minus 2z squared plus 4z minus 8. Wait, is that the polynomial? Oh, no, never mind, that is the polynomial. But normally I think I cheated too hard, since, of course, this could be a complex number. But anyways, that was the answer, so that's cool. And on to the next one. And the next one is, oh, no, not that. We have f of the function is equal to 3z cubed plus 4z squared minus 4z plus 7, where z is equal to 1/2 minus square root 3 over 2 I. Okay, so we know the complex conjugate is also the root, remember? So we have z minus 1/2 plus root 3 over 2i times z minus 1/2 minus root 3 over 2i. So let's factor this out. So we get z squared minus z, since we have minus 1/2 here, minus 1/2 here, and then root 3 over 2i cancels out. And finally, we need to multiply these two together. So we have plus 1/4, and then we have root 3 over 2i times root 3 over 2, negative root 3 over 2i, which is 3/4. So this is z squared minus z plus 1. This is going to be our root. And so we need to get 3z cubed plus 4z squared minus 4z plus 7. And actually, I was thinking about it, and the way we did it last time wasn't technically cheating. We know that since this already has an order 2 polynomial, in order to get to an order 3 polynomial, we only can have one more root. And if we have a complex root, then its conjugate must also be a root, and since that doesn't work out, meaning our remaining root has to be a real number. So here we have 3z cubed, so we know the first one is 3z, and the back is 7, so we have plus 7. So yeah, that should, pretty much be our root, be our factorization. Yeah, that's correct. So this is the factorization. And then let's move on to another question, and that one will be, we have f of z. is equal to z to the 4 plus 5z cubed plus 11z squared plus 13z plus 10, where z is equal to negative 2 minus I. Okay, so let's get our quadratic. And so we have z plus 2 plus I and z plus 2 minus I. So we have z squared plus 4z plus 5 as a factor of this larger polynomial. And so now we can divide it here. We're going to have to do long division though, since this is a quadratic. I guess we could have split it up and done synthetic, but it might be hard since we have complex roots. Anyways, z to the 4 plus 5z cubed plus 11z squared plus 13z plus 10. So we have z squared here, so z 4 plus 4z cubed plus 5z squared. And so we subtract, and so we get z cubed plus 6z squared plus 13z. So we can put plus z here. So z cubed plus 4z squared plus 5z, and then here we can subtract and we get 2z squared plus 8z plus 10. And of course this leaves our remaining factor as plus 2. So we need to factorize z squared plus z plus 2, and you could factorize it on the spot, but the easiest way to do it is the quadratic equation. So we have negative 1 plus or minus the square root of 1 minus 4 times 2 times 2, so 1 plus 8, all over 2. It's equal to negative 1 plus or minus, remember this is going to be the square root of, minus. This is going to be square root of 7. So this is going to be square root 7i all over 2. So, wait, do we have to factorize it, or we have to find the remaining zeros? Oh, okay, so the remaining zeros are just this. So it's negative 1 plus or minus square root of 7i. Is it negative? Yeah, it should be negative. Negative b, yeah. All over 2. It's a bit weird that the book says it's not negative, but I'm pretty sure it is negative. So, okay. Anyways, on to the final few questions. And so the first question is, given that z is a 0, find the missing coefficients, find all the remaining zeros, and check your answers. So we're given z is equal to 2, and the f of x is equal to x cubed plus ax squared plus x minus 2, where of course a is a real number. So if we need to find the missing coefficients and all the remaining zeros, okay, so we can find this coefficient by synthetically dividing by 2 and making sure the end result has to be 0. So here this would be 1, 1, this is a, 1, negative 2. So a, this is times 2 to 2, so this is a plus 2. So this is 2a plus 4, 2a plus 5, 4a plus 10, so 4a plus 8 is equal to 0. So a is therefore equal to negative 2. So that is the missing coefficient. And we need to find the rest of the roots, given that 2 is a root. So we need, if a is equal to negative 2, then this turns out to 1, or I guess 1, z squared, 0, and 1. Yeah? So, I mean, this is z squared plus 1. And so we need to find the roots of z squared plus 1. Of course, they're not going to be real numbers, but we can straight away tell that this is going to be equal to plus or minus I, since this is the only root that would work. So that is the missing root. And on to the last question of today. And the last question is similar. So we have z is equal to square root 5 I, and the function is equal to x to the 4 minus 2x cubed plus ax squared plus b of x plus 85, where a and b are real numbers. Okay, so we know that one root is going to be square root 5i, and therefore negative square root 5i must also be a root, since the conjugate must be a root. So if we have, this would be equal to, this means z squared plus 5 is a factor, and so we can simply factor this out. A, b, okay, yeah. And it's quite easy to find a and b. We just do long division, so this is z to the 4 minus 2z cubed plus az squared plus bz plus 85. Okay. So first we have z squared, so we have z to the 4, and then we have plus 5z squared. So we have negative 2z cubed, and this would be a minus 5z squared. And so if we factor this out again, minus 2, so this is going to be minus 2z. So we have, this is minus 2z cubed, and then because bz minus whatever we subtract, which is in this case negative 10z, has to be 0, b must equal negative 10. So let's make a note of that, b equals negative 10. And next we have the final one, where we have a minus 5z squared and plus 85. So we know that this must be a factor, so it must divide to 0. So in this case, we need to divide 85 by 5, which gives us 17. So we know that this actually has to be plus 17. And so if we have 17z here, well, a minus 5 must equal 17. So a must equal 22. So a equals 22, b equals negative 10, and find the remaining roots of z squared minus 2z plus 17. So there's no way that that factorizes into a real number, so we plug it into the quadratic formula. 2 plus or minus the square root of 4 minus 4 times 1 times 17. So in this fact, this is negative 4 times negative 16, or negative 64 over 2. So this will be equal to 2 plus or minus 8i, or 1 plus or minus 4i. And so this is the remaining root. So yeah, that was it. I hope you enjoyed the speedrun, and I hope to see you in the next one. See you then.